let's take a look at this question right here. Bohr's model predicts that the two lowest allowed energy levels of hydrogen are negative 13.6 and negative 3.4 electron volts. So if you have if we were to draw an energy scale right here, so this is 0 over here, negative 13.6 is going to be down here, electron volts. Okay, so that's your lowest allowed energy level. That is called your ground state. Like the lowest floor of a building is the ground floor. And then after negative 13.6, the next allowed energy level is negative 3.4 electron volts. So that's about a quarter of 13.6. So negative 3.4 is over here. Okay, so that would be called your first excited state. Okay, so when an atom, okay, of hydrogen absorbs a photon, so you have an atom right here, a photon comes in, and the atom absorbs it, we say the atom is excited. So that means the atom gains energy. The energy of the photon becomes part of the energy of the atom. So you have an excitation over here from the ground state to the first excited state. So this process whereby a photon is absorbed by an atom and is called excitation. Okay? So what wavelength must this photon have in order for it to be absorbed by the hydrogen atom in this situation? Well, the answer is that you're going to need 10.2 electron volts for your photon energy, and that would correspond to 122 nanometers. So let's see how we figure that one out. Okay? Well, if you recall, the energy of the photon, okay, would be the energy that would be gained by the atom. So it has to be E upper minus E lower. Okay? So we know we are given the E upper is negative 3.4 electron volts and E lower is negative 13.6 electron volts. And that's equal to, if you recall, hc over lambda, where h is Planck's constant and c is the speed of light, and so you can solve for lambda. Okay, so let's first calculate E upper minus E lower, and this should be, and it should be easy for you to figure that out. That should be 10.2 electron volts. We can change that to joules if you want. In fact, we should, and so we can change that to joules. You can change that to joules, and you should remember that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. Okay. Anyway, let's solve for lambda from this equation over here. You can see, if you rearrange this equation, you can see lambda is just equal to hc over your E photon. Okay, and so let's go ahead and do this calculation. H, Planck's constant, is 6.626 times 10 to the negative 34 joule times seconds. Speed of light is 2.998 times 10 to the 8 meters per second, divided by the energy of the photon, which is 10.2, but an electron volt is 1.602 times 10 to the negative 19 joules. So that's 10.2 electron volts, okay? And this makes it easy to do the cancellation. You can say joule cancels out, seconds cancel out. Your answer here will be in meters. So let's plug those numbers in. Bring up a calculator here. 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th divided by 10.2 divided by 1.602 times 10 to the negative 19. That gives me an answer of 1.215, 3 sig figs, so 1.22 times 10 to the negative 7 meters. Okay, And we can change that to nanometers. What's a conversion? 1 nanometer is 10 to the negative 9 meter. Nano means 10 to the negative 9. Okay. And this gives us an answer of 122 nanometers. So that would be light in the ultraviolet region. So you can't actually see that light. Or conversely, if you say if a hydrogen atom goes from the first excited state to the ground state, it's going to produce ultraviolet light, which you're not going to see because it's not visible to you. Okay?